The purpose of this video is to determine the dynamic effects of spring rates on standard and high-performance vehicles. The constraints will be that testing will mainly determine the effects of spring rates on under and oversteer in a race car setting. We will discuss the difference between stiff and soft springs, how ride comfort is affected, and the spring rate setup on a race vehicle. Springs are a multi-purpose tool used in the suspension of a vehicle, allowing for precise handling, ride comfort, and load bearing. Springs are used in relation with shocks as part of the suspension of a car. Here, a torsion bar is shown. It is generally preloaded by either a clockwise or counterclockwise twist. Torsion bars are not interchangeable, so they can only fit into the vehicle for which they were designed, a large disadvantage. Leaf springs date back to the very first automobiles. In a leaf spring, the amount of leaves control the stiffness. How they are held in place will determine their endurance. The most common type of spring, and our test subject, is the coil spring. The coiled wire twists during the spring's compression and extension cycles. As you can see, they take up a small amount of space, which is a great advantage.
Spring rate is the criteria used to describe springs by measuring the constant amount of force it takes to extend or compress a spring a certain distance. For example, if a force of 10,000 newtons is applied to a spring and it vertically compresses 1,000 millimeters, the spring rate would be 1,000 newtons per millimeter, force over distance. This graphical representation of the spring rates show the top line is a much stiffer spring, while the lower line has a much softer spring rate. There are advantages and disadvantages of both soft and stiff springs. One benefit of a softer spring rate is an increased time of contact between the road surface and the tire on rough road surfaces, increasing safety and handling. The benefits of stiff spring rates are typically seen in race settings and include reduced body roll, lower clearance, and better aerodynamic efficiency. The stiff spring contributes to the roll stiffness of the car and its ability to resist dive under braking, squat during acceleration, and body roll during cornering.
One of the dynamic effects we observed was how varying spring rates affect the ride comfort of a vehicle, which is a main concern when designing the suspension system of a vehicle. Springs with lower spring rates are used on stock vehicles as they provide a much more cushy ride comfort, making it more comfortable for the driver and any passengers. Lower spring rates equate to softer springs, meaning it takes less force to compress the springs, allowing the vehicle to move easier over bumps and other road non-uniformities, improving the ride quality. The negative of having soft springs is that they are not optimized for cornering ability or weight transfer, which is of more importance in race vehicles. As you can see in the video, the vehicle with stiff springs does not adjust as much over bumps, providing poor ride comfort. The vehicle with softer springs, however, does adjust over bumps. However, if this vehicle's springs are too soft, it will adjust too much over bumps, providing poor ride comfort as well.
When setting up a race car, you select springs to add or subtract weight and essentially steering or drive force to get the right amount of oversteer or understeer. The stiffer a tire's spring is, the more weight transferred to that tire in the turn. When doing an analysis for a circle track car that only turns left, for the rear axle, we look at the rear drive force for each tire. When one drive force is larger, this creates a moment around the center of gravity. As seen here, when a larger driving force is on the right rear, a positive moment is created, helping the car turn left more and creating oversteer. The opposite can be observed when more drive force is on the left rear tire. This creates understeer. When analyzing the front axle for understeer or oversteer, we look at the component of the force facing the rear of the car. As you can see, that a large force on the right front creates a negative moment and understeer, while a large force on the left front creates a positive moment and oversteer. In this video, understeer is observed because the wheel is turned very far to the left and the car does not turn as much. In this video, oversteer is observed because the driver has to countersteer a significant amount at the exit of the corner.
Simulations were conducted using NASCAR 2015. This game gave us a great testing platform as it allowed us to make spring rate changes while keeping the rest of the setup constant. One assumption that needed to be made was that the driving style was consistent from one race to the next. We were able to analyze how changing the spring rates affected the handling of the vehicle through the use of in-game tire wear readings as shown in the video, and the driving response through the force feedback steering wheel. The other source for our results was through a real-life circle track racing experience. After lots of testing at many different tracks and our real-life racing experience, we found that a softer spring in the right front and the left rear makes the vehicle understeer, and a softer spring in the left front and right rear makes the vehicle oversteer. There are many components that affect the handling of a vehicle, but other than spring rate adjustment, our testing assumed all else constant. We researched how different spring rates affect a vehicle's handling and ride comfort. We also studied the direct impact that spring rates have on racing vehicles. The studies were backed up by simulations and personal experience.